All right, I know you guys are all super excited. We're going to start the talk. So find your seats, grab your friends. If you're out at the bar and you can hear me, come on in and listen to the talk.
Thank you, Craig. Everybody hear me okay? All right. So hello, welcome to my talk. Thank you to the organizers. Really glad to be here. Great opportunity. Really appreciate the venue and great organization, great cause, cybersecurity, of course, which we all depend upon for our prosperity. So there's going to be two parts of my talk. The first part will be about the risk of quantum computing, and the second will be about data integrity framework. So my primary goal, I'm going to have two goals. My primary goal is to convince you, first of all, that these are two important cybersecurity problems that we can start to do something about today. And the second goal is hopefully to get you guys to see the connection between the two. All right. But first, a little bit about myself. So I was born and raised in Iowa. Grew up here, went to Iowa State, partly because the digital computer was invented up there by John Vincent Nassau and Clifford Berry. At Iowa State, I chose to do 2 degrees simultaneously in 2 different colleges. So I went there for computer science and also for business finance. After my undergraduate degrees, I went on to get a PhD in computer engineering, also at Iowa State. And after that, went on to work for the seed company, Pioneer Hybrid. While I was there, I worked on digital automation, pipelines, basically data pipelines, building software tools, visualization tools to help the geneticists there pull out insights that were important for the business. After Pioneer, I went on to work at Scientific Games. It's a company involved in, basically gaming. I worked doing some research into game personalization and also worked on some models for doing acquisition, monetization, and retention of customers. After Scientific Games, I worked at Bayer Crop Science. Worked at Bayer Crop Science doing a number of different things: data engineering, digital automation, software engineering, cloud engineering, a lot of different things, including getting involved with some leadership activities, doing mentoring, and a number of collaborations. Along the way, I ended up getting a master's of business administration, and I also worked as a associate director for the board of directors of Greater Iowa Credit Union. Now, a little bit about my family. So I'm married, have 2 daughters. My wife, Kimberly, is on the left. Here's a picture of us at the Grand Prismatic Spring in Yellowstone National Park. Great place. We love to travel. My 2 daughters, Sophie and Ellie, they are incredibly intelligent. They have great character, and I'm very proud of them. So a little bit more about my sphere. So my mother actually was the first woman to get a master's degree in computer science from Iowa State. My dad got a PhD in physics and invented Powerball. My brother got a PhD in computer science, went on to work at a company you're all familiar with, Discord. And interestingly, he ended up being bestowed the key to the city of Des Moines. And one of his friends as well, one of his schoolmates, who ended up starting a genetics company called Pairwise. And not just that, one of his other schoolmates, one of his other friends, ended up starting Pinterest. All right, so why am I here to talk to you today? Basically, I'm seeing some pattern that's really scary. And so about 10 years ago, James Comey, former director of the FBI, said that there are 2 types of big companies. Big companies that know they've been hacked, big companies that don't know they've been hacked. And if you fast forward 4 years from there, you're looking at a hardware hack that supposedly affected as many as 30 companies, including Amazon and Apple, and thousands of their machines. And this was a very sophisticated hack. Basically, they took a chip and put it on a motherboard, and in some situations, they even put it between the fiberglass of the multiple layers. So this is a chart here describing the last 20 plus years in terms of the amount of cybercrime that's been reported, according to the FBI. And this has been trending upward this whole time. So even with 10 years ago, us knowing that there's a major, major problem, we are still seeing issues. And this is just the cybercrime that's been reported. So last year there was $12.5 billion of damages. This year there's going to be even more. And this is just the tip of the iceberg. So of the reported damages, that's only accounts for about 20% of what there actually supposedly is. And not just that, there's probably some things that we're not aware of. All right, so now a question that I ask myself is, are we the underdog? Because today we do have problems in cyber assurance. And it's not completely unreasonable to understand why. Because for every one of us in cyber assurance, there's about 50 or more adversaries trying to get into the windows, the doors, the cracks, the crevices that we're all supposed to be defending, okay? And sometimes cybersecurity isn't respected for what it is. It's relegated to patching. But there's so much more to cybersecurity. Confidentiality, availability, integrity, all important. And we saw a preview of what can happen when the availability system is taken down. So with the CrowdStrike incident, that impacted availability of airlines, emergency services, government systems, and more. Just imagine what could have happened if that was intentional. So I'll be focusing mainly on a couple risks to confidentiality and integrity. So let's talk about what's at risk. So think about what we all take for granted. Many of the systems that were affected with the CrowdStrike issue, money, banking, airlines, 911, all these things we take for granted, the availability of the systems could be taken down. Not just that, but think about our competitive advantage in the world, the confidentiality of the trade secrets in high-tech industries, medicine, agriculture, material sciences. Not just about availability and confidentiality, think about the integrity of critical infrastructure. So critical infrastructure like utilities, water, electricity, things that we take for granted, hospitals, communications, because our prosperity is not a given. Think about our way of life. Our prosperity depends on confidentiality, availability, and integrity. Our national security depends on cyber assurance, and our way of life depends on you. So let's talk about mitigating the risk of quantum computing. So quantum computing has potential to help us gain competitive advantage in many industries, from biotech, materials, finance, medicine, and other industries. But it also has the potential to break encryption protocols across the internet. And without post-quantum mitigation now, today's data may already be compromised by the time quantum computing becomes a reality, because there's implications for today's data, and there may be implications for cyber insurance issuers. There may be implications for the integrity of cryptocurrencies. So we need to do something now. So let's take a look at what a typical vulnerability consists of. So typical vulnerability, there's a period of time where we think that we are, thanks. A period of time where we think that we are safe. There's an exploit that appears in the wild, so perhaps a day zero, and then there's a period of time that we think we're vulnerable, after which we apply a patch and we hope that we're safe after that. Now, quantum computing is a different beast altogether. So today's data that can be valuable many years into the future, in some ways, the period of vulnerability for that has already begun. And once an exploit is available, historically recorded data can be decrypted and the content of communications can no longer be trustworthy. So we need to apply quantum safe encryption as early as possible. And to make this argument, let's look at our risk scenarios. So here I have a grid. On the top are two events or two possible events that could happen that we don't control, okay? And on the left side, there are things that we can potentially do, all right? So on the top, it's either the RoQ, this risk or rise of quantum happens, or it doesn't happen. And on the left, we either do nothing or we do something, all right? Now, what happens if there is no rise of quantum computing? Because that is technically possible, right? So if we don't do anything, we lose nothing, we gain nothing. On the other hand, if we do something, we might waste some effort, right? We have all priorities, there's different things of importance, but if the rise of quantum does happen, and we lose the confidentiality of information, and we lose the integrity of systems and data, we're essentially looking at a game over scenario where we do lose our prosperity. So if there is mitigation, if we choose to go that route, then we can fight for cyber assurance and for our prosperity so that it continues. So which choice should we make when the worst case, if we do nothing, is that we could lose our prosperity? So if we want to minimize the worst case, which choice do we make? I think we should choose to do some mitigation, okay? So now, one problem is, do you think we should just switch over to post-quantum cryptography? Anybody? I don't think so either. So with post-quantum cryptography, if we were to change over directly to post-quantum cryptography, there's a lot of things that we just don't have the experience with right now. We don't have experience with the encryption protocols, the signature protocols, the algorithms, the key generation, implementation, all of the places that there have been vulnerabilities in the past. And that is a problem both if the rise of quantum doesn't happen or the RoQ does happen. So what else might we do? Some people say hybrid. Anybody heard of this? Hybrid cryptography? So there's a lot of things that could be meant by hybrid cryptography. We could think about there being part of a key being generated using traditional cryptography. We could generate part of the key from post-quantum cryptography. Another possibility that hybrid could mean is that we're using post-quantum digital signatures and traditional cryptography. And you could probably think of a number of other ways, such as hybrid algorithms themselves. So not just hybrid keys or selection of different parts of cryptography, but the algorithms themselves. But what I'm going to suggest is that we could go at it from what I'm calling an onion approach, okay? So as an onion kind of brings to mind, you can think of kind of layers, okay? So what are three parts typically in a cryptographic communication? Can anybody tell me? Go for it. Those are three parts. I'm going to break it down a little bit differently, but you're right. So there's an authentication algorithm. Talk about it in algorithms. Okay. There's a key exchange, and there's the symmetric encryption. So typically we think about public-private key stuff, both handling authentication or digital signatures along with the key exchange. But I've kind of broken it out this way because with post-quantum, you got to think about things a little differently. So, all right. So how many of you have heard of forward secrecy? All right. And some people call it perfect forward secrecy. Can anyone tell us what that means? All right. I hope everybody heard that. I'm not sure I'm going to be able to repeat it quite right, but basically, if we have a key that's broken, future keys are not compromised. Now, typically, this is in the context, we talk about this in the context of sessions, so communication sessions, but I'm going to talk about it in terms of algorithms, because quantum computing runs the risk of breaking algorithms. Okay, so what happens if each of these components break? So if our digital signatures are broken, then that means that we risk somebody impersonating us, okay? If the key exchange is broken, we lose confidentiality. And if their symmetric encryption is broken, the algorithm for symmetric encryption, then those sessions become vulnerable. And all of these are things that can be affected by quantum computing. All right, so now if we go back and think about, I mentioned record now, decrypt later. So if we're talking about record now, decrypt later, what do you think is the most important component here to think about changing? Anyone? So the most important is going to be the key exchange. It's based on your typical public-private key cryptography. It's said to be the weakest link if quantum computing were to become a thing. And what is another potential part? It's the symmetric encryption. So many communication protocols today use 128-bit cryptography or AES cryptography for their symmetric encryption. The bit strength, or the number of bits, would be reduced by half, basically 64-bit instead of 128-bit. All right, so, and more generally then, record now, decrypt later. What will we need when an era of quantum computing becomes a reality? Because we can get by right now if we want to defend against record now, decrypt later. We can get by with post-quantum safe key exchange and symmetric encryption, but we can't, and we don't need to change authentication at the moment. But if we were to go into the era of quantum computing, we need to change them all. So now, I mentioned one of the problems is that we don't have enough experience today with post-quantum algorithms and implementations, and some might be vulnerable. There are multiple, not just digital signature algorithms, for example, but there are multiple candidates, some of which have been approved by NIST, some have not. And it's important to note that our communication layer is only as strong as its weakest link. So what should we pick? Let's see. So, yeah, if any one of these three components is broken, we can lose confidentiality, integrity, availability. So how do we best mitigate against changeover or the risk that changeover represents? So here are three possibilities for a communication layer. Okay, in the pink or the red, there is what we have today. In the yellow is a possibility for doing or preventing or resisting the record now, decrypt later. And in the blue or green, cyan, there is something that can be helpful when we get to the quantum era. So if we were to design communications today, how would we minimize risk? So my suggestion is going to be define an onion. So with an onion, I'm going to argue that it's basically a nested approach, so that to help us mitigate the limited understanding of PQ algorithms and their implementations. All right, and what can we do? Since we don't know enough about the algorithms and implementations, we could add multiple layers. So we can add multiple layers, we can mix and match layers, but basically by the outcome is essentially that if the RoQ doesn't happen, then we're no worse off than our post-quantum implementation. And in the case that the RoQ does happen, then we have the strength of the onion's strongest layer protecting us. Everybody like that RoQ thing, or I don't know, there's some. All right. So, which approach to mitigation do you think makes the most sense? Whether we're going to pick PQ changeover or the onion approach. If your executives, for example, are accessing strategy documents on your corporate network from a hotel, internet, or if there could be eavesdropping on your communications to and from and within the cloud, or if you're using wireless at home or from a coffee shop. So I think it makes the most sense to do something, and that something is to keep in place what we have today for the moment and add a layer with the intent of this being the start, not the end, of protecting against the rise of quantum computing. So what can you do today? So avoid introducing additional risk where possible. There are post-quantum VPN solutions. Post-quantum tunneling is another possibility. If I have time, I might be able to demonstrate. And then use the onion approach, add layers as prudent. Obviously don't want to introduce any availability risk, but if you have important data, and not everybody will have important data that might be useful into the future, but if you do have important data, use post-quantum encryption to help reduce that confidentiality risk for record now, decrypt later. And remember that if you do take a step in that direction using post-quantum encryption, but not post-quantum digital signatures, that you'll need to make an additional change at some point in the future as well. All right, so I said there was two parts, okay? So we talked a little bit about the important security properties, confidentiality, availability, and integrity. So in the data engineering world, there's been an acronym. I'm sure you've heard of it because it's been tossed around a lot. There's been a lot of work in this area for this last several years. Basically, this acronym FAIR, findable, accessible, interoperable, reusable, corresponding to data. It's basically gotten a lot of attention, mostly focused on availability and accessibility of data, because if you can't use it, you can't get the benefit of it. And so one thing that organizations have been doing to embody this FAIR acronym is to bring the data together, put it in an analytics repository or database. All right. So let's talk about some of the ways that we get data into an analytics repository. So some of the approaches include things like replication, ingestion, mining of data, and there's other ways too. And there's also lots of different data sources. So, and these different data sources we may have different degrees of trust in. So we could have data that comes from an internal source, like a transactional database or some other operational database. There are log or streaming data that we could get from a number of different applications. And there is obviously data that we might be getting externally from our partners or websites, and others as well. So some of that data that we get, even if it's coming from internal sources, some of it we might consider good, and some we might consider bad. But what does it mean for data to be bad? Well, in many cases, the dialogue in the past has been about, is it true or is it false, which is a hard thing to answer. What's more measurable, better ways to measure might be in terms of accuracy or precision, and there are tools that are being used to indicate accuracy, which is how frequently something is correct, and precision, which is how bad it is when it's off or when it's wrong. But I'm going to talk about it in different terms. I'm going to talk about two different types of bad data. The first type being data that doesn't fully conform to expectations, and the second being data that causes impact without a known origin. And at the root of both of these types of bad data is low integrity. So low integrity data is expensive. And so anybody have an idea? Well, I think I put it in the advertisement, but I was going to say, anybody have an idea of how much it costs an organization? So on average, according to Gartner, bad data costs an organization about $13 million a year. And bad data leads to, and this cost comes from outages. It comes from lower productivity, comes from higher maintenance costs, and bad decisions. So now I'm going to talk about how improvements to data engineering, right? How did I get on this data engineering? I'm going to talk about how improvements to data engineering can help improve cyber assurance. Okay, so let's start walking through a typical data engineering scenario. So when we think about data engineering, this is pretty much what everybody thinks about. There's some smart guy or smart woman comes up with idea or data, produces that data, hands it off to a data engineer, and that data engineer then hands it off to a data consumer, data scientist, data analyst. Now, there's a problem with that. In reality, things are a little bit more complicated. So with type 1 bad data, the problem is that data that might be good, a data engineer or a data consumer might say, hey, this doesn't make sense to me, or they can't fit it in. Somebody created this record, but they don't know what to do with it. And so that data can sometimes get lost. And in addition, there's type 2 bad data. The problem is that somebody who finds a data source, maybe it's external, they say, hey, someone might be able to use this. And so they hand it off, goes into the system, and at some point, it's possible to be elevated to fact. So this boils down to essentially separating what I'll call the gold from the garbage. And it's a difficult problem. So to illustrate, let's think about April Fool's Day, okay? So if I have 3 of your friends tell you something, who knows best whether that data is gold or garbage, whether that pattern that you might see is accurate or not? So what I'll say is that you as the data consumer might not be in the best position to determine whether it's fact or fiction. So I'm going to say you're not the subject matter expert of the data. You're the data consumer, you're on the receiving end. What about your 3 friends? Do they know the accuracy of the information? Well, maybe they do, and maybe they don't. Are they willing accomplices, or are they unwitting accomplices? And are the data and they can be thought of as messengers. Essentially, the data engineers they are not the subject matter experts of bad data. So who knows best what should be expected? Who knows the accuracy, the basis in fact of the underlying data? Well, if I told your 3 friends to tell you, it's going to be me, right? It's going to be the data producer. So maybe it was or maybe it wasn't an April Fool's joke. But let's start by talking about the type 1 bad data, okay? So there's a lot of reasons that data might not conform to expectations. Simple things like, it's the wrong type, missing field, definitions can change, out-of-bound values. Some might be accidental, other situations might be intentional. but data that doesn't conform can't be considered good data, and it can create problems. So what are some clues, for example, if we were talking about April Fool's Day, that might lead us to suspect that that data is bad? Anybody have any? I'll offer my own thoughts. So I would say that it could be that it is April Fool's Day, right? Context is kind of important. You know, maybe if it's April Fool's Day, there's a greater chance that that there's going to be a joke played on you. There could be inconsistencies between what has been told to you and facts or patterns that you know. And not just that, but the quality can vary based upon where the data is coming from. So if these are 3 of your best friends forever, then they might be more likely to play a joke on you than if they're just 3 acquaintances that you just recently met. So what are some of the common practices for handling non-conforming data that might have inconsistencies? So here are the 3 common approaches, really. One is to halt data ingestion. The second is to discard the data. And the third is to change all of the data to strings. It might be a number, but if a character shows up, now all your data is strings. So what are the consequences of these actions? So if you halt data ingestion, then you're going to impede the availability of data and systems, and people and processes can't get their work done. Anyone tell me a recent example where a system halted, caused an availability issue? Yeah, so CrowdStrike. And now, what if instead we were to discard that file, that data file that described how to detect and understand and mitigate against vulnerabilities? So we can't throw away data and hope that it's not important, because if it were the CrowdStrike file, well, we wouldn't be able to detect and handle those problems. And the third approach, the consequence of essentially passing the buck, right, changing all of the data to strings, you're creating a problem for somebody else, because now instead of that data being strongly typed data, it's now strings, and everybody downstream, any data consumer, is going to have to do the same or handle the same problem that you almost handled, but they're going to have to do it again. And not just that, but I would suggest that when preconditions are not satisfied, it's not okay either to basically unilaterally change a data interface. So sometimes each of these 3 practices might work. You know, maybe I'm doing something for myself, or maybe it's an ad hoc analysis, or who knows what it is, but none of these common practices are the right thing to do all the time. Okay, now we all know code needs testing, and we all know that code needs to be resilient. But just as important, I'll argue, is that we need to validate not just code, but data and configuration. Because we wouldn't, for example, put jet fuel in a Nissan. So at least we wouldn't expect it to work. So we need to validate the data, and issues that we find need to be reported. Because there's also a risk to the integrity of a system, as we talked about just a moment ago. If, for example, the CrowdStrike sensor that used the data file silently failed, we wouldn't be detecting or handling the vulnerability, and nobody will be any the wiser. All right, so the solution, I'll suggest, is that we reimagine data engineering and change the paradigm. So what I think we need is an agreement between data producers and data consumers that describes what's acceptable and what's not, so that when mixed quality data is produced, that data is triaged, separated into good and bad data according to some pre-agreed approach. Because it's not a one-size-fits-all approach. and we can tailor then how we handle the data to the specific nature of the need. So maybe we will put the data in anyway, maybe, if it'll go in. I mean, I don't know how you put well, I guess you could put a number in a string, but maybe not a string and a timestamp, right? Maybe you'll throw it away. Maybe you'll fix the data. Maybe you'll set it aside and log it. Maybe you'll improve the process that data was generated or produced, or how it was extracted. And instead of potentially important information ending up in the trash, a data steward, who's a subject matter expert in that data, can determine what to do with it. And a table steward can capture the expectations and facilitate the agreement between that data producer and the data consumer. Kind of like an API for software, but it will be a data consumer or producer-consumer interface, essentially. So that the data engineer is no longer expendable, but the data engineer is a key facilitator that can save a company millions of dollars. Instead of halting operations, we ensure that they continue. Instead of discarding data, we report it to a subject matter expert to figure out what to do with it. Instead of passing the buck, we provide a robust interface between who's producing the data and the people using the data. And instead of finger pointing, we can get everybody on the same page. All right, now there's a lot more that goes into reimagining the paradigm to help detect, manage, and handle type 1 bad data. And it can help reduce availability issues as well as ensure the integrity for downstream partners. All right, so let's put type 1 data, bad data aside for the moment, and let's talk about type 2 bad data. So I'm going to give another illustrative example. So let's talk about AI, okay? So with AI, it's said to build models based on mining books, your emails, your documents, social media posts, as well as websites. And besides the obvious confidentiality concerns that your ideas and your personal information may no longer be private, but the integrity of an AI is only as good as the data it was trained on. So it makes what I'll call a Trojan butterfly effect, kind of a crisscross between the two there, not so unrealistic. So if you probably all know what a butterfly effect is, but just I'll explain it just anyway. So butterfly effect is that a butterfly flaps its wings on one side of the planet, creates a hurricane on the other. Okay? So if someone or something written by somebody who's halfway around the world in an otherwise private email or social media post is used to build and impact an AI model used by your business, can you confidently say that that model will not hurt a valued outcome for your business? And more directly, is it important to control the origin and the accuracy of information used in your organization? And more generally, in the age of AI, how do we ensure the transparency of our business decisions? So I will argue that we need reproducibility and traceability. So let's talk about a typical analysis pipeline. So your typical analysis pipeline is going to have your data source, some data input, could be your analytics repository. It has an analytical workflow, maybe a pipeline of sorts, and it produces some output, some record or records. Now, given this process, I'm sure you can all think of two problems where that will make reproducing data difficult. Okay. The first is going to be if the data source changes, then we can expect there's going to be a potential change to the resulting data as well. And similarly, even if the data stays the same, if the code changes, then we can expect that the results can change as well. And this happens all the time. So what can we do to best ensure the reproducibility of results? We can capture snapshots of data and well-defined code. Now, it sounds complicated. I'll get to it in a bit. I think you'll find it pretty simple. But how might we go one step further and not just be able to reproduce the results? That one step further being traceability of results. So we can annotate resulting records with what I'll call run information, basically identifiers for these snapshots of code and data. And with traceable data, we can understand how decisions were made, and in some ways, we might solve, both the traceability and reproducibility problems. So how might we snapshot data? So a simple way is if we are using the analytics repository, then we can basically describe a snapshot with a timestamp. So if we have lots of files coming in, replication data, database, we had timestamp, and what are some ways that we could, did you have a question? Okay. And what are some ways that we might snapshot code? So it's interesting because, of course, there's Docker images, Docker hashes, and we can record the images, the hashes, and the mapping of data to arguments. All right. So now back to, let's see. All right, so now we have, let's say, a solution to type 2 bad data. And if we control what goes in other words, the data that we accept into our organization, and we have the solution to type 2 bad data, we can get traceable, reproducible results that increase decision transparency and improve quality assurance. And if we combine type 1, or the solutions to type 1 bad data and type 2 bad data, then we have a data integrity framework that solves bad data problems. Done right, it can save an organization a lot of time, money, and headaches, and help digitally orchestrate an enterprise. So I hope that I have achieved my primary goal, which is to convince you that data integrity is incredibly important, especially in the age of AI, deepfakes, and misinformation, where we might not be able to trust the information coming from outside our organization, and that there is something that we can do about it to start making better decisions. Second goal, back to the beginning. I mentioned that the two parts of my talk are connected. Anyone have a guess how to connect them? All right. So if we were to combine a data integrity framework with post-quantum digital signatures, we might even build a trustworthy blockchain or blockchains of data analyses. Thank you. Any questions? Yes. So I'm not getting into that because I don't think we know enough. Oh, sorry. I'll repeat the question. The question was, what's the time frame for quantum computing to become a reality? So I don't think that we know enough to answer that question, but there are people that are making estimates, end of the decade. But don't rely on my word for that, I would say. The point is, though, that some organizations do have data, trade secrets and what have you, that need to be protected many years into the future. And whether quantum computing becomes a reality in the US or abroad in the next 5 years or more, some places need to keep their trade secrets longer than that. We need to be preparing if you have that important data. Yes. So the question, I believe, if I, correct me if I misstate it, but the question is, it's easy to understand what it means when code changes, and Docker images are a way to capture code images. What's uncertain is how we capture a snapshot of data. So there are a number of databases or analytics repositories that do support, and for that matter, you build your own, but that do support what they call time travel. So time travel is essentially you have a timestamp. You can go back to any point in time to determine what that data was at that point in time. So you can do a query, reproduce that data, and so any updates that have happened to the data, new data or changes or deletions even, don't affect what you see at any particular snapshot. Any other questions? Well, thank you, everyone. Really appreciate it.